Okay, so this problem, 1639, so it just says design a fourth order bandpass using a de Leon-Friend circuit with gain adjusted to 1, using RA and RB for each second order section. And so they give us the transfer function, and so each fraction represents a second order bandpass. When I bring up like my little note cards for my different types of filters, you can see this one was for band stop. And the numerator looks like s squared plus a constant squared. But I want you, it's more important to focus on the denominator when we're starting out. But as you'll see, the denominator is always the same. So looking at the numerator tells you what kind of filter it will be. The denominator is going to help you find your omega naught and your Q. So if it's s squared plus a constant squared in the numerator, it's band stop. If it's just a constant or a constant squared in the numerator, it's a low pass filter. Notice it's the exact same denominator, If it's s squared, nothing added, then it's a high pass filter. And then there, again, same denominator as the three other types, but this time it's going to be a constant times s in the numerator, and that would be bandpass. And you see, that's what we have in these two, constant times s. So we know each of them is a bandpass, but like I said, focus on the denominator, and I would do the constant first. So omega naught is just going to be the square root of the constant term. So in this problem, there are two sections, right? So for the first section, omega naught is the square root of 3.4143 times 10 to the 8th. Which is 1.8478 times 10 to the 4th. And then you look at the coefficient of s. That's what's going to help us find our Q. Because again, if you look at regardless of which type of function is, the coefficient of s is omega naught over Q. So that was bandpass. Low pass, omega naught over Q. High pass, omega naught over Q. Band stop, omega naught over Q. So regardless of which type of filter it is, the coefficient of S is omega naught over Q. So for the first section, we get omega naught over Q equals 4072. So think of like basically cross multiplying, and you'd get 4072 Q equals omega naught, but you want to solve for Q, so divide both sides by 4072. But we know what omega naught is, so then we can find Q. I get 4.5378. And then for the second section, same process. Omega naught is the square root of the constant term. So I get 1.2819 times 10 to the 4th. And then for this one, omega naught over Q is 2825. So Q is omega naught over 2825, but omega naught for this section, we just found it. And I get 4.5377. Okay, so I get the same value basically both times for Q. Okay, and then on my card, I put the values of, so this R equals 1, the R1 and R2 are equal to each other. So for the normalized, R1 equals R2 equals 1 ohm, and that's for both sections. And then the Q was the same. It was just rounding, but it was the same. So the C, again, I'm guessing C1 and C2 are equal since I only put C. I didn't separate them out. So I'm just going to do 1 over that 4.5377. And I get 0.2204. Farads. Oh, R2 equals 4Q squared. So this must only be R1. R2 equals 4 times Q squared. And I get 82.3629. Okay, and then to make it have a gain of 1, we have to find this R sub little a and R sub little b. So, whoops. R sub little a is just 2Q squared, so it would actually be half of what I just found, because I just found 4Q squared. So this is going to be 1/2 R2. So 41.1814. And then R sub b is 2Q squared, which is what we just found. So I'm just going to call that, so it's RA over RA minus 1. And I get 1.0249. Okay. So nope. The Q was the same for both sections. Okay, so for the normalized part, they should all be the same. But then when we're doing magnitude and frequency scaling, then for the resistors, so, and this is regardless of which type of filter you have, R new is always just equal to Km times R old. And I think Dr. J I think she did that in her video, talks about the magnitude and frequency scaling. And then for the capacitors, it's C old over Km times Kf, and Kf is just omega naught. So that's going to be different for the two sections because they had different values of omega naught. I have the answers down here. Let's see. Yeah, they didn't give normalized, but we can check the resistors right now. 82.3657. Yeah, it is just a little bit of a rounding error. So my R2, and that's kilo ohms because I'm multiplying by 1,000. And notice this is basically the same. Remember my one was 0.77 and one was 0.78. I was lazy and I just called it the same. And then 1.0249. Is that what I got? 1.0249. And then R2, 82.3657. Yeah, I already talked about that one. I think I checked off the 41 point, oh no, that's it. Okay. So now I have to find the capacitor values. And they do have C1 and C2 equal, which is what I also had. Okay, that's fine. Okay, so let's find for the first section. C new equals, so for the first section, oh, they have the same value of Q, so that part was fine, 0.2204. Divided by Km, they tell us is 1,000. And then for the first section, omega naught was 1.8478 times 10 to the fourth. And I get 1.1928 times 10 to the negative 8. Okay, so I can move the decimal over one spot and make it 10 to the negative 9, and then it will be nanofarads. And this is 5.9632, but that makes me think, okay, well, that's like half. That's because when I was finding this, I just did 1 over Q. I didn't do 1 over 2Q. So if I do 1 over 2, so I should have had 0.1102. And so if I divide that by 2, then I get 5.964 e to the negative 9, so times 10 to the negative 9th. So that's 5.964 nanofarads. Okay, close. That was for the first section. And then the second section, remember, just our omega naught changed. So this is going to be 0.1102 farads divided by 1,000 times. And then the omega naught for the second section was 1.2819 times 10 to the fourth. And I get 8.5966 times 10 to the negative 9, which is 8.5966 nanofarads. All right, that's it.